Okay, I started the recording this time. Well, I'm glad that nobody was still in the Teams with me yesterday when I realized that I forgot to start the recording because I said things that were unbecoming of an instructor. But in the end, I guess what I did was I just I went to my other class and then I came back and I re-recorded the entire lecture over again. So if you're a YouTube instructor, or if you're a YouTube student, then you got a slightly shorter version of the lecture, and that was just by nature of, well, there was no students for me to ask, do you guys understand what's happening, or to ask, you know, any other questions, I guess. So that's re-recorded. It's up on the YouTube channel. It has the same content in it. And hopefully I never forget to start the recording again. But I'll ask all of you guys who are my regular people in the actual teams, if you see me start the lecture without recording, please tell me. And please try to remember to start the lecture for me, because if I forget again, I'm going to be really sad. All right, how's everybody doing otherwise? Yeah, I know. That's the thing, is that most students, I guess if you're in here, probably, or maybe you do watch the recordings every now and again to review and stuff. Okay, cool. Okay, so how are all of you? You guys surviving, making it through? Nice. Haiti surviving this week. Slow week for Savannah, man. That's unusual. I've been having a really opposite of a slow week. But that's true. We get Friday off. That'll be nice. Okay, well, surviving's the most important part. Then at least you can have an opportunity to focus on thriving. Yeah, Friday off. That'll be nice. 3-day weekend. Okay. Well, I'm glad to hear that at least everyone's surviving. Someone had their hand up a while ago. I'm not sure if that was by accident or not. Was there a question about anything, or should we start? Okay, it doesn't seem like there's any questions, so let's start. Oh. Okay. So here's a couple announcements for today. Office hours today from 9:30 to 11:30. Okay, so if you're confused about any of the stuff we've been talking about so far, or if you want a little bit more review on angles or specifically geometry, okay, because we are going to use a tiny bit of geometry to do this trig stuff. Mainly what we're going to use is just, how to find the circumference of a circle, how to add up the interior angles of a triangle, how to use the Pythagorean Theorem, and so on and so forth. So we'll be drawing a little bit of triangles and a little bit of circles, and we'll be using a little bit of geometric deduction in order to kind of help us understand this trig stuff. So if you're a little bit hazy on that stuff, I'd recommend you come to office hours today and we can talk over everything that you could possibly need to know about geometry in order to do trigonometry. There's a homework still due this Friday. I just don't want anybody to get confused because we had the exam on Monday. There's still a homework due on Friday. It's over some of that logarithmic and exponential equations. Also, exit slips are due after each and every lecture on a 1-week delay, okay? So after today's lecture and after tomorrow's lecture and every lecture thereafter, there's an exit slip on Blackboard, which you need to fill out, okay? It's pretty short. You can just do it right after you watch the lecture. If you're in person or if you're on the YouTube, then, you know, right after you watch the YouTube video, just do the exit slip. I'm not sure why, but there's kind of, well, let's just say there's a non-zero number of students in the class who have not done like a single exit slip, and I'm really kind of confused because it's worth 7% of your grade, and I'm not sure I can communicate that any more clearly. So if you don't do any of the exit slips, the highest grade you could possibly get in the class would be at 93%. So I mean, I guess you could still get an A if you were really good at everything else. But yeah, just, you know, get those free points. It's just completion. Okay, and then the exams, I haven't started grading them. I'm going to start grading them probably today. And my goal is to get them done by the weekend so that I don't have to grade exams over the weekend because I have other work that I need to do over the weekend. But we're just gonna have to see. So it'll either be, probably they'll be posted either on Friday or on Monday. Okay, so that's about the exams and administrative stuff. So any questions about that? Oh, there is a question here. Are we going to have a math homework this week with the wellness holiday Friday? Yes, you will have a homework this week. Suppose I could make it due on Monday again if you guys don't want to spend the wellness day doing homework. Would people want me to do that? I'll think about it. Okay. All right, well, let's start in. So let me remind us what we were talking about last time before we get into the new stuff. So what did we talk about last time? We started with basically the most simple thing that we need to understand in order to do trigonometry, which is what is an angle. Okay, so it's a way to quantify the difference in direction between two rays. Okay, and we had two different units for being able to do that. So just like we measure things, the length of things in feet or meters or inches or centimeters or whatever, okay, we have all these different units for length. We just decide that a certain amount is one unit of that particular type of length. And somewhere out there, there's a meter stick, which is the meter stick, right? Which is like, that's how long a meter is. And basically we do the same thing with angles. We just decide that, okay, an angle which looks kind of like this one is just 1 degree, okay? And everything else is just built up of, you know, possibly multiple of these things kind of stacked on one another. Okay, so that's what about degrees. And then we also learned about a couple special angles like right angles, acute angles, obtuse angles, angles of greater than 360 degrees. So we can go all the way around and then some. And negative angles as well are okay. We talked about kind of how to draw these angles by referencing their relationship to a 90-degree angle. And then we started talking about radians, okay? And radians are just a different unit of measurement for angles. And the nice thing about radians is that 1 radian an angle of 1 radian produces an arc length or a pizza crust length of 1 unit. Okay, so if the unit circle is 1 meter in radius, then 1 radian of an angle in the middle of it will produce a slice of pizza whose pizza crust is 1 meter long. Okay, that's how radians work, which is kind of clever, I think. It's kind of like measure to be just the number that we get when we check its arc length on the unit circle, which the unit circle is really important, and we use it all the time to do all sorts of things, including the rest of all of trigonometry. So this is kind of like a great way to define, or a great way to quantify angles. Okay, so that was about radians, and then we just talked about how to kind of think about radians, how to draw radians, angles that are measured in radians, that is. Negative radians are also fine. And then we had this conversion chart where we learned a bunch of different ways we can write special angles in degrees and radians. And we also talked about how to convert between degrees and radians, okay? And the key to converting was this equation that 2 pi radians is equal to 360 degrees. And we can convert between any number of radians and any number of degrees by just manipulating this equation. Or you can memorize the cheat code, which is that if you want to move from degrees to radians, you just multiply by pi over 180. And if you want to move from radians to degrees, you multiply by 180 over pi. Okay, and if you want to remember how to keep these straight, okay, one thing that you might think of is that pi over 180 is some number which is much less than 1. Okay, so it's going to make our number smaller. And that makes sense if we're moving from degrees to radians, because a radian is like a, 57 degrees or something like that. So if we have some measurement in degrees and we switch it to radians, we better wind up with a smaller number than we started with. And likewise, if we start with radians and we move to degrees, our new number should be much larger than we started with. And so when we multiply by 180 over pi, well, that number is larger than 1. So we're going to get a number which is larger than what we started with. And if we multiply rather by pi over 180, then we're going to get a number which is smaller than what we started with, which is consistent with what we expect based on the fact that 1 radian is approximately 57 degrees. So that was about going between. Oh yeah, we also had a comment about pi and 180, which is to not get confused about pi being equal to 180. We actually have that pi radians is equal to 180 degrees. This equation is true, but this one, pi is equal to 180, is not true. Okay, pi is actually a number itself. It's like 3.14 da-da-da. So we can only set it equal to 180 if we modify each of these with a degree, okay, or a radian. All right, and then lastly, we talked a little bit about finding coterminal angles, and basically the result of that conversation was that if theta is an angle, then if alpha n is defined as being equal to theta plus 360 degrees times any integer, okay, then alpha n and theta are coterminal. Okay, so if we just have theta is some angle, well, you can just go around an extra 360 degrees, and then that's also coterminal. Or you can go around an extra 720 degrees, and that's also coterminal. Or you can go the other direction in 360 degrees, and that's also coterminal. Okay, so that's all that this is saying. Nothing fancy. It's just saying that, you know, if I do 5 spins, I wind up in the same place as if I did 4 spins. Or if I do 3 spins, or 2 spins, or 1 spin. Or 1 spin and then a quarter spin is the same as 2 spins and then a quarter spin, is the same as 3 spins and then a quarter spin, and so on and so forth. So this is about coterminal angles. Okay, so I'm pretty much done reviewing what we did last time, and now I'm going to do this last example, and then we'll move on to something else. Okay, so this was the last example that I didn't have time to get to, so we're going to do it now. So here we have the, oh, it's not quite the unit circle here. We have a circle of radius 2. Okay, we have a circle of radius 2, and I have an angle in here of 30 degrees. I have an angle of 30 degrees. And I want to know, what is this arc length L? Okay, what is this arc length L? So maybe this is a good one for us to think about as a class. We technically have all the tools that we need to do this problem. So maybe we can think about how we might find this arc length L. Okay, so we want to know the length of the pizza crust if our pizza angle is 30 degrees. So where's maybe a good place to start? Can anybody get me started off? What might be some useful information to know first if we're going to be concerned with arc length? Convert the degrees to radians. That would work pretty well, I think. So let's try that. So first of all, 30 degrees times pi over 180 is equal to, well, we cancel out 30 from pi and 180, and we get pi over, let's see, divide 180 by 30, we get 6. Okay, so we can express this angle here as pi over 6 radians. So here's a question for the class. Yes or no question. This angle's pi over 6. Therefore, the arc length is pi over 6. What do we think? Two yeses, any no's? Aha, I think Aeon's kind of got the crux of it. Our radius here is 2. We said that an angle of 30 would produce an arc length of, an angle of pi over 6 radians would produce an arc length of pi over 6 length on the unit circle. So let me draw the unit circle in here. Here's the unit circle. So what we actually know is that this length here, so if we imagine that this is a unit circle, radius 1, then what we really know is just that, I'm running out of colors. How about red? No, pink would be good. Oh, I already used pink. We'll use purple. We know that this length is pi over 6 units long. But we're interested in this length here of L, and it seems like maybe if we had a pizza which was twice as, or yeah, which had a radius which was twice the size of our original pizza, then the crust is going to be a little bit longer. right? So how can we quantify this? How should we proceed now? Is there a way we can overcome this obstacle? Yeah, I think multiplying by 2 is probably going to be a good bet. But let's verify. Here's what I can see geometrically, just looking at this. I can see that although pi over 6, this purple length, and this pink length are not the same, they are proportional. Okay, they are proportional. Proportional to what, you might ask? Well, pi over 6 takes up the same proportion of the entire circumference of our circle as L should take up of the entire circumference of the larger circle. So I can set up a proportion here as follows. Well, I know that the radius of the inner circle is 1. So its circumference should be 2 pi times 1. So I can set up that pi over 6 divided by 2 pi. And here this 2 pi is the circumference of the inner circle. And how can I set this equal to? Well, I can set this equal to, well, the thing that I want to know is going to be L. And then in this denominator, I should put the circumference of the outer circle. Now, our outer circle has radius 2. So its radius is going to be, or its circumference is going to be 2 times pi times the radius, which is 2, so 4 pi. And now I can just solve this equation. I can multiply both sides by 4 pi. On the right side, it just cancels, and on the left side, we're left with just 2. And we get L will be equal to 2 times pi over 6, which is equal to pi over 3. Okay, so it turns out everyone was right. We should just multiply by 2. Okay, we should just multiply by 2. However, I'd like everybody to take note or to notice how I came to that conclusion was very mathematical. Okay, I started with something which I knew, and I took baby steps to get from there to show that we can just take that arc length and multiply by 2. Okay, so I'm just going to say that a lot of the time these geometric things can be misleading. Okay, for example, if you consider our circle here, our circle system here, if we have circle B and circle A, we have that the circumference of A is equal to 1/2 of the circumference of B. That one's true, but what's not true is area of A is actually equal to 1/4 of the area of B. Okay, so a lot of the time, okay, these geometric things, we don't necessarily have a relationship that says, well, this radius is 1 and this radius is 2, so everything is just double. It's not necessarily going to always be like that. So this is the reason why we should take this mathematical approach and try to frame things a little bit differently, and take our baby steps to get to where we want to be. Okay, so jumping straight from pi over 6 to pi over 3 might be it worked out this time, but it might be a little bit of a treacherous maneuver on account of, you know, not everything with double radius has double everything else. Okay, so that's just a word of caution, but that's a great way to figure out this arc length here. Okay, another way we could have done this problem is by recognizing that a 30-degree turn is 30 over 3/60th of the circumference. 30 over 360 is like 1 over 12th of the circumference. And then we would use 2 pi r to get the circumference, and we'd get 1 over 12 times 4 pi equals pi over 3. We could have also done it that way. Okay, so you can think about the pizza crust as being like a percentage, a certain percentage of the entire circumference. And the percentage will be the same as the percentage of this angle from the entire 360-degree turn. So that's one other way to think about this problem. Okay, any questions about this example? I think this was a great problem. Okay, no questions? Then we're going to move on. And before we talk about trig in a little bit more detail, I just want to remind you guys of some rules about triangles, and in particular about special right triangles. Okay, so first of all, if we have a triangle, the angles inside the triangle always sum to 180 degrees. So if we have a triangle like this one, okay, then we take 45 plus 45 plus 90, and we get 180. Okay, so the angles inside of a triangle always add up to 180 degrees. And if you measure them in radians, then they sum to pi, just to pi. Okay, because 180 degrees, if we translate that to radians, we'd multiply by pi over 180. Okay, so if I did 180 times pi divided by 180, we would cancel these and we would just get our pi, okay? All right, so that's the first fact. Second fact is we have the Pythagorean Theorem, which says, basically, if we have, this is only for right triangles, by the way. So it only works if one of the angles in our triangle is a 90-degree angle. So like one of these guys, okay? So we got to have this 90-degree angle in order to use the Pythagorean theorem. But if we have a right angle, then we can say that if A and B are the lengths of the legs, okay, so if we have A and B here, then the length of the hypotenuse is given by the square root of A squared plus B squared. That is what the Pythagorean theorem says. Okay, a squared plus b squared equals c squared. So in particular, if we know two of the side lengths, we can figure out what the other one is pretty easily by manipulating that equation. That's the Pythagorean theorem. And then there's two special right triangles. Okay, there's two special right triangles. And I want to remind you guys of the special properties of these triangles, which are the following. First of all, if we have a 45, 45, 90 triangle, that's how we call this. Or sometimes, I guess, if we were to write it using radians, okay, it would be, well, this one would be pi over 2, this one would be pi over 4, and this one would be pi over 4. Okay, so if we have a right triangle with these two angles being equal to one another, then these two sides will also be equal to one another. Okay, these two sides have the same length. So in particular, if this one has length x, then this implies that the other one also has length x. And these two together imply that this one has length square root of 2x squared, which would be equal to square root 2 times x, or x times the square root of 2. Why don't we write it that way? Okay, so for example, if we have a 45, 45, 90 triangle and they tell us that this length here is 6, we can figure out the length of the other sides pretty easily by doing the following. Well, we know that if this is x and this is x, then 6 is equal to x times the square root of 2, and therefore x is equal to 6 divided by the square root of 2, which we would then rationalize the denominator, and we would get that x is going to be equal to, let's see, 6 root 2 over 2, which is equal to 3 root 2. So then we would say, okay, if this one's 6, then x has to be equal to 3 square root 2, and then the other side length is also 3 square root 2. Okay, so this is a review of 45, 45, 90 triangles. If we know any one side, we can find out all the other sides. Okay, just by using this fact. They will always have the form x, x, and x times the square root of 2 goes on the hypotenuse. So that's a 45, 45, 90 triangle. And there's another triangle which is important, which is the 30, 60, 90 triangle. It has a similar thing going on, except all the side lengths will be different, but they'll all obey kind of a nice property, which is that if the side length across from the 30, which remember, the side length across from the smallest angle will be the shortest side length. So if this one's x, then the side length across from the 60 will be x times the square root of 3, and the side length, which is across from the 90, will be 2x. Okay? So, for example, if we had a 30, 60, 90 triangle, and we knew that this length was 3, the hypotenuse was 3, then we could figure out what x is by taking that and dividing it by 2. So this side across from the 30 would be half of that, which would be 3 halves. And then we would just take that number and multiply by the square root of 3 to get the other side length, would be 3 square root 3 over 2. Okay, so this is a review of special right triangles. Hopefully this is review for everybody. I can't spend any more time on it, but if you need more review about these guys and you always struggled with this, please come to office hours. Okay, so finally, we're going to talk about the unit circle and trigonometry trigonometric functions, which we usually just call trig functions because that word is obviously very hard to say. So let's talk about the unit circle. So here's actually a rigorous definition of what the unit circle is. It's the circle of points defined by the equation x squared plus y squared equals 1, which if we remember from our section on circles, this would be a circle with a center at 0, 0, because remember the center is like, we have this equation x minus h squared plus y minus k squared is equal to r squared, right? And we said that the center would be at h comma k. Well, we're not subtracting anything here, so h and k are both 0. Hopefully that's clear. And also our radius has the property r squared is equal to 1, so r is equal to the square root of 1, which is just 1. Okay, so the radius is 1. Okay, so it looks like this, and we have the circle passing through the points 1, 0, 0, 1, -1, 0, and 0, -1. Okay, so 4 points which are on the circle, and the center is at 0, 0. So this is what we're working with. And so here's a quick question which we can use to test our knowledge of circles, which is the following. Is the point 2/3, negative square root of 5 over 3 on the unit circle? Someone tell me, how can I test this? How to test if a point is on a circle? What should I do? We had an exam question on this, I think. Crickets for checking. Well, maybe I can give you a hint. The points which make up the graph of this circle are going to be the points x, y, which satisfy this equation. So if I want to check if this one is on the graph, what should I do? Yeah, we can just plug it in. We just plug this into this equation, and we see if we get something which is true or not. So let's try. We get 2/3 squared plus -5, or negative square root 5 over 3 squared. We check, is this equal to 1? Well, 4/3 we'd get, or 2/3 we'd get 4/9 plus the square root of 5 squared is 5, and the negative sign goes away because we squared it. The new denominator is 9, so we get 9 over 9, and that's equal to 1. So yes is our answer. It's on the unit circle because it obeys the equation which defines the points on the unit circle. Okay, so that's how we can check that. All right, so that's just a quick review of circles. Okay, and now we're going to define our trig functions. Okay, so if you pay attention to one part of this entire lecture, this is the part that I pay attention to. And here's how we define them. We define this function p of theta. Okay, so p is a function which takes an angle as an input, and then the output is a point. Okay, so p of theta is a function which takes an input of an angle and an output is a point. And we say we let x comma y, so the point that gets outputted, is going to be the point on the unit circle which lies on the terminal side of the angle theta measured from the positive x-axis. Okay, so we start at the x-axis. Okay, we start at the x-axis here. We measure theta, okay, and we get our terminal side. And our terminal side just, kind of goes on and on forever, right, because it's a ray. And we take the point on the circle. Okay, we take the point on the circle, which our terminal side intersects the circle at. Okay, and we call that point x comma y, and we say that it's the output of our function p. Okay, so we take a theta, we take an angle theta, we plug it into the function p. Okay, so we have our function p here. In goes theta, and out pops x comma y. Where x comma y is on the terminal side of theta and on x squared plus y squared equals 1, the unit circle. Okay, so this is p of theta. Okay, so it's just describing the point on the unit circle which corresponds to any angle. Okay, so if we had a different angle here, maybe it looks like this, then this point x comma y corresponds to the angle gamma, or beta. Why don't we call it beta? Okay, so we have this other angle beta, then this x comma y is going to be equal to p of beta. Okay. This actual notation of calling it p of theta and saying that it's a function is less important than the fact that x comma y, this point, corresponds to the point on the unit circle that we get when we measure an angle of a certain quantity and find that point on the unit circle. Okay, so that part's not that important. Okay, then, here are our big ones. The most important trigonometric functions are that sine of theta is equal to the y component of the point on the unit circle, which corresponds to our value theta. Okay, so if we want to know what sine of theta is, we do the following. We draw our unit circle, we measure our angle theta, then we find the point on the unit circle, we say that is the point x comma y, and then sine of theta is just the y component. Okay, so if you think about it, it's also the height of the triangle that we would get if we were to draw in this point here. We'd have that this is y units tall, right? And we would have that this is x units wide. Okay, so if we draw that triangle, then sine of the angle theta will be the height of the triangle that we get by inscribing it inside of the unit circle. Okay. Likewise, cosine theta is just going to be the x value that we get when we do the same process. Okay, so we start with an angle, Then we draw it. Then sine will be the height of x comma y on unit circle. Okay, same thing on the other side except width. Okay, so these are sine of theta and cosine of theta. So let's do a quick example. So say we want to find sine of pi over 4 and cosine of pi over 4. Okay. So the very first thing we would do is, oops, don't want to get rid of that. Oh, there we go. The very first thing we would do is we'd draw in our angle, pi over 4. And I know that pi over 4 is equal to 45 degrees. Okay, 45 degrees. So here's what I'm going to do. I'm going to draw in this triangle here, which is inscribed in the quadrant where our point actually lies. Okay, so I'm just going to consider this quadrant 1, if you remember. And I'm going to inscribe this triangle by dropping a line to the x-axis. Okay, we always drop our line to the x-axis when we're drawing this triangle. Okay, so if we were over here, we would draw it like this, so down to the x-axis. And if we were in one of the other quadrants, like this one, we would draw it up. Okay, so the one we draw in always goes to the x-axis. Okay, so you can remember that by remembering that the dotted line should always be vertical. Should always be vertical. Okay, then we're just going to use some geometry here to figure out what these values are now. Erase this business. So we know that this is the unit circle, and I know that this ray, which starts at the origin and ends on the end of the circle, should have length 1. And I know that this triangle in here has a 45-degree angle here, and I know that it has a 90-degree angle here, and I know that it has a 45-degree angle here because the angles inside a triangle should add up to 180. So I'm left with the following problem. My task is to find sine of pi over 4 and cosine of pi over 4. And I know that sine of pi over 4 is going to correspond to this length here. The height of this point is sine pi over 4. And the width of this point, or the x-coordinate of my point, which, God, can I draw this properly? Okay, this one's going to be cosine of pi over 4. So let me draw this in a little bit expanded form. We have basically a 45, 45, 90 triangle where the hypotenuse has length 1. And that's equal to x times the square root of 2, and then these other side lengths will be x and x respectively. So if I solve for x, I get x equals 1 divided by the square root of 2, which is equal to square root 2 divided by 2. And so that's my answer, basically. I get that sine of pi over 4 is actually going to be equal to cosine of pi over 4. And those are all going to be equal to square root of 2 divided by 2. So that's how I actually compute sine and cosine. I'm just looking for the side lengths of these triangles. Okay, so we've only had one example. We'll do some more examples next time. So I'm going to close with that for today, but I'll say that I have office hours starting now and ending at 11:30 a.m. So if anybody wants to talk about more trig, stick around, or if you have questions about geometry that you don't remember it too well, also stick around. Otherwise, everybody have a great day. Yep. Do we have exit slips for this week? Oh, that's a great point. No, I better post those. Thanks for reminding me that. Slips. Okay, I'll upload those immediately. Okay, so they should be up within the next 10 minutes or so. Sorry about that. Yeah, and then I was even sitting here telling you guys, like, please complete the exit slips.
How dare you?
I know, right? Okay, yeah, I'll get those. Yeah, no, you're not off on your days. I'm just off on my game. Let's see, exit slips. Okay, let's see, assignment. Morgan, did you have anything that you wanted to talk about?
Yes, everything.
Everything, okay.
So lost. I wasn't able to look at the video from yesterday, but everything you just taught just went right over my head.
Okay, well, we'll get back to it then in 1 second. Let me put this due date here for this exit slip. That'll be Tuesday, submit. And we'll have week 9 exit slip Wednesday. It'll be due on the 17th, and it'll be worth 1 point. Submit. Last one. James 18, 1 point. Submit. Okay. So let's talk this stuff over then. And let me switch really quickly to my headphones. Okay, so where should we start? All the way at the beginning?
Sure.
Okay, so maybe I can give you a brief recap of what we talked about last time as well.
Okay.
Okay, so I'm going to go through this stuff, and what I'd like you to do is stop me at any point where you're like, wait, I don't understand that, okay? And I'll zoom in and talk more about it, all right? Okay, so here's our basic principle. We have this angle here, okay? So there's these two things going in a different direction.
Yes.
Okay, And the first thing we want to do is decide how we quantify, how we use a number to describe the difference in direction between these two things. Okay, so if I had a third ray, which is coming out like this, then I want to be able to say something like, well, the difference in direction between ray 1 and ray 3, so this one's ray 3, here's my ray 1, the difference between ray 1 and ray 3 is kind of like twice the difference between ray 1 and ray 2.
Okay.
Does that make sense?
Yes.
So we're trying to quantify this difference in direction. Okay, and we call this quantity an angle measure. And we have two ways of measuring the angle. We can use degrees or we can use radians. Okay, so first of all, we have a positive angle and a negative angle being given by counterclockwise rotation and clockwise rotation, respectively. So if you look at these two angles, going from ray 1 to ray 2 or from ray 1 to ray 3, they're both what we call positive angles because the rotation is opposite that of the hands of a clock, right? This would be like time going backwards. We call that counterclockwise rotation.
Okay.
Okay, if we go the other direction, if we go like this, from ray 3 to ray 1, then the red angle is called a negative angle.
Okay.
All right. Good so far?
Yes.
Okay. So how do we actually measure them? Okay, first I'll talk about coterminal. So two angles are called coterminal if they end on the same side. Okay, so if we start in the same place and we end in the same place, then these angles are called coterminal. So if we take this angle theta here and we compare it to the angle beta, even though they're very different, right? One of them's going up, one of them's a positive angle and one of them's a negative angle, and the difference is pretty large between like how far we're going to rotate, right? But what this is saying is that if they're coterminal, then the end result is the same. We wind up facing the same direction.
Okay. So the circle ends in the same direction. Is that what we're saying? Or the angle?
So here's how you can think about it. If you imagine this as a bird's eye view, okay, and this yellow circle here is the top of my head.
Okay.
What we're saying here is I'm initially facing this direction. Okay, so my eyes are looking in the initial direction.
Okay.
Now imagine if on the spot I spin and I start looking, I spin this much so that my eyes are now facing in this new direction. Okay. Then the angle measure is a quantity, so it's a number, which describes how far did I spin.
Okay.
Okay. And here's what it means for angles to be coterminal. It means that if I start looking in this rightwards direction and I turn this much in this direction and I'm then facing in this terminal direction, then that is somehow the same end result as if I were to spin a little bit further in the other direction, and then I would still be facing in the same end direction.
Okay.
So an angle is sort of measuring like how far did I spin, right? You might have heard somebody say like if you do a 360 or if you do a 380 or a 180 or whatever, right? That means you either do a full turn or a half turn or whatever, right?
Yeah.
Okay, so this is referring to angle measurement in degrees.
Okay.
Okay, so if we have a degree, it's somehow expressing an angle measurement, okay? And what we say is that we define 1 degree to be 1/360th of a full revolution. Okay? So if I turn 360 degrees, I've turned all the way around.
Okay.
So if you imagine me here, if I turn 360 degrees, I've turned all the way around. But if I just turn 1 degree, then I've turned 1/360th of the way all the way around.
Okay.
So that is a degree. Okay. And then here are some special angles with particular measures. Okay, so first of all, this angle here is a 90-degree angle. It looks like a perfect corner.
Mhm.
Okay, so the angles in the corners of your house or your apartment or your dorm, they're all 90-degree angles, probably.
Okay.
Okay, and we call an angle acute if its measure is smaller than 90 degrees. Okay, so something like a 50-degree angle would be an acute angle. And they look like these kind of sharp turns like this.
Okay.
All right, let me check in. We still good?
Yes.
Okay. Conversely, an obtuse angle is one that's not acute. Okay, it's going to be larger than 90 degrees.
Okay.
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 The next step is taking this a little bit further. We can also have angles which are more than 360 degrees. Okay. So if I do a 405-degree spin, what that means is I do a full 360 and then an extra 45.
Okay.
Does that make sense?
Yeah.
And if I were to do negative 405 degrees, well, that means I do a 360 in the opposite direction, and then I go an extra 45 degrees in that opposite direction. Okay, so here we can see the difference between 405 degrees is not the same as negative 405 degrees. The direction which we choose to spin kind of matters.
Okay.
Okay. And just to bring back that coterminal aspect, okay, we have that 405 degrees is coterminal to 45 degrees. What does that mean? Well, that means that if I start right here and I spin in an entire 360, okay, spin an entire 360, and then I go an additional 45-degree angle, then I'll be facing the same direction as if I had just started initially and turned only 45 degrees.
Okay.
Sorry, go ahead.
Okay, so this coterminal is like kind of throwing me off.
Okay. So coterminal is just a word which we use to describe the relationship between two angles. Okay, so we would say something like one angle is coterminal to another angle.
Okay.
Okay, and it has to do with their sides. So if we have one angle which starts here, we call this the initial side.
Yes.
And then we call this the terminal side. Terminal means ending, right? So if we have our angle going up like this, then this is an angle where this is our terminal side.
Yes.
So two angles are going to be coterminal if we have the following. So say we have another angle over here, which is a different angle. And this angle says, well, we take our initial side, we spin all the way around, and then go a little bit more than that, and end up on this terminal side.
Okay.
Okay, so when I talk about this spin here, what I want you to visualize is something like this in this GIF here. You see what I mean?
Yeah.
That's what I mean by spin. It's like the hand of a clock going around. Okay, so if you imagine we start on the same thing as our initial 0 degrees, and we go all the way up, around, all the way around an entire revolution. Okay, so we start here, we go bam, 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 rotate all the way around until we hit a full revolution, and then go a little bit further. And we wind up on this terminal side.
Okay.
Okay, when we say that these angles are coterminal, what we mean is basically, if I put these angles on top of one another, well, I didn't do a very good job of drawing them coterminally, but they should be going eventually in the same direction at the end.
Okay.
Okay, so even though these two things are fundamentally different processes, right? You would say, if you saw somebody stand here and spin 45 degrees, and you saw another person stand here and spin 405 degrees, you wouldn't say that they did the same thing, but you would say that the end result is the same. They end facing in the same direction.
I'm Dee Howery. I work with Wyatt in Salesforce. And we set up processes.
Is that clear?
Make sure everything
Yes.
properly within Salesforce.
So here's another example. Imagine a clock which only has a minute hand. There's no hour hand on our clock.
Mm-hmm.
So say we start and the minute hand is facing 3. Okay. 1 hour later, 1 hour later, the minute hand is again facing 3. Agree?
Yes.
How about 2 hours later? Where's the minute hand facing?
3.
3 again. Okay. So what was the total spin for 1 hour? How many times did we go around?
Once.
Once. So how many degrees is that?
360.
360 degrees. Okay, great. And then in the 2 hours, how many times did I go around?
2.
Twice. So how many degrees is that?
It wouldn't be 360, would it?
Not 360. You ever heard of Tony Hawk?
Yes.
What's Tony Hawk famous for?
No.
He had one trick that was like his most famous trick ever. Ever heard of it?
That is a 720.
Okay, well, yeah, well, that's what our trick is here. This is going to be 720. He was famous for doing a 900, which was three whole spins, or no, 2.5. Yeah, 2.5 whole spins. Anyways, that was just to get you thinking about degrees in terms of spins. So this one's 720 degrees. So these two processes are different, right? One time we went around once, and one time we went around twice. What it means for angles to be coterminal is just that the minute hand is facing in the same direction at the end.
Okay.
Okay, so even though these are different angles, one of them we went around once and one of them we run around twice, we call these angles coterminal, because at the end the minute hand is facing in the same direction.
Okay.
Okay?
Okay.
Cool. So here's some information about how we draw angles. Okay, so usually we just kind of think about how much of a right angle is our angle. Okay, so for example, if I want to draw a 45-degree angle, I know that 45 is half of 90. So what I can do is I can just draw a 90-degree angle, which I know how to draw because it's just a perfect corner. And if I want to draw a 45-degree angle, I just draw an angle which looks like half that much.
Okay.
Make sense?
Yes.
Likewise, if I had a 30-degree angle, 30 degrees is 1/3 of a 90-degree angle. So if I wanted to draw that, it would be like I'd draw a 90-degree angle, and I would imagine this being cut into thirds, right? And then I would say that this is a 30-degree angle. Okay.
Okay.
Okay. Or I can think of larger angles being multiples of right angles. Okay. So 270 degrees. Okay. Is like 3 right angles altogether. So I start by drawing this first right angle, this green one, and then I draw this orange right angle, and then I just draw this red right angle, and I put all those back to back to back, and I say that doing a 270 is like doing 3 90s.
Okay.
Okay, so this is the end result would look something like this.
Okay.
Okay. All right. So next up, we defined radians, okay? So radians are essentially just a different unit of measurement for an angle, right? So you work in, or you're trying to get your medical degree, right?
Yes.
So probably you guys measure fluids in medical practice using things like milliliters or centiliters, or you might use like metric measurements for things, right? Like grams,
Yeah.
or milligrams. Okay, but in the United States, you probably grew up learning to measure things using like ounces, fluid ounces, or pounds, or kilograms, or not kilograms, but you see what I mean, Fahrenheit. Okay, so we have these different units of measurement, right? And we have ways of comparing them. So we just say that, like, this length is 1 foot, and it's just kind of arbitrary how we decide how long a foot is. We just decide how long a foot is, and then we describe everything else as being however many times as long as that, right?
Okay.
And then we have a meter, right, which is longer. And somewhere out there we have a meter stick, which is the meter stick. And that's just how long a meter is, and everything else is just a proportion of that, right? It might be 2 meters or 1.5 meters or half a meter long, right?
Yes.
So the same deal works for degrees and radians. Okay, we have 1 degree, which looks like this. Okay, it's very small. It's 1/360th of a full revolution. So if I lined up 360 of these all together, then that would get me all the way around to where I started. Okay, and a radian is a little bit different. A radian is more like a meter, where one radian is a much larger unit of measurement than a degree is, okay? And here's how we define a radian. We say that if we take 2 pi of them, then that takes us all the way around. Okay? So if I have an angle, here's 1 radian, here's 2 radians, 3 radians, 4 radians, 5 radians, 6 radians, and then a little bit extra, because 2 pi would be like 6.28.
Okay.
Okay, so here's 1, 2, 3, 4, 5, 6, and then finally 6.28 gets us all the way around.
Okay.
Okay, so we defined a degree by saying that 360 of them get us all the way around. We define a radian by saying that 6.28 of them get us all the way around.
Okay.
So it's just a different unit of measurement. Okay, so this is our end-all be-all equation here. We have that 2 pi radians is a full circle, and so is 360 degrees. And this is how we relate these two equations. This is kind of like how back in the day you might have learned how to convert degrees from Fahrenheit to Celsius, right? The way you derived that equation was by using the fact that 212 degrees Fahrenheit is when water boils, and 100 degrees Celsius is when water boils, right?
Mm-hmm.
And so if you take those two units of measurement and you relate them, you have this kind of common length. And this is kind of like your Rosetta Stone for understanding how to relate the two quantities, right? So it's kind of like, you know, if nobody knew how long a meter was and nobody knew how long a foot was, then you could just take some unit, something which everyone knew how long it was. Like you could say, I don't know, like a football field is this many meters and this many feet. Then you could figure out the conversion between the two, as long as you have this center reference point. So for our case, the center reference point is 1 full revolution, and we say that 1 full revolution is 2 pi radians or 360 degrees.
Okay.
And we can use this equation to figure out how many degrees is 1 radian. Okay, by dividing both sides by 2 pi. Okay, so if we take 360 and we divide it by 2 pi, remember 2 pi is something like 6.28.
Yeah.
And we'd get that 1 radian is something close to 57 degrees.
Okay.
Okay, don't memorize this. This is not to be memorized.
Okay.
This just to give you an idea. And then 1 degree is something like 0.017 something radians.
Okay.
Okay. And here's why we use radians. Okay, degrees just came from the fact that we've always used degrees forever and ever, and it's just you know, something that we use. And then somebody much later on thought up radians, and everybody thought, wow, that's way better. We should have been using that from the start. But we can't quite shake this degree business, so we teach both.
Okay. Question.
Mm-hmm.
So if we're given like, say we're given like, I don't know, like 45 degrees, how can we write the 45 degrees in reference, like when trying to get radians with that equation?
I'm about to get there.
Okay.
First, let me tell you what a radian actually is.
Okay.
Okay. A radian is defined in the following way. If we take the unit circle, okay, which is a circle whose radius is 1 unit. Okay, so the radius is 1 unit, so the diameter would be 2. You good about that?
Yes.
Then a radian is defined in a sort of a clever way. We say that 1 radian is the angle such that if we put it in the middle of the unit circle, then the crust of our pizza slice is exactly 1 unit long.
Okay.
We call that crust the arc length. So that's how we define what a radian is. And it's sort of clever because then we know, basically, as long as we know the circumference of any circle, we can compute a radian, or we can compute what the angle is just by checking, what is the arc length of that thing, which is a rather easy thing to measure, right? I would just stand here with my tape measure, and I put it on the ground, and then I would walk over to here, and then I would, place my tape measure down, and I'd measure how long that was, and then I would be able to tell what is the angle between these 2 points in radians.
Okay.
As well, and it should match up with the lead itself.
Okay, so that's what a radian is. Okay, so how do we switch between? Here's a table of common values, which you can switch between, which you can always refer back to. Okay, but I'll give you the cheat mode for how we actually switch between these two. Usually what we would do is we would just take this equation and manipulate it until we have what we want on one side.
Okay.
Okay, so we take our 2 pi radians equals 360 degrees. So say we want to know what 20 degrees is in radians. We just divide both sides by 18. If I divide the right-hand side by 18, I'll get 360 degrees divided by 18 would be exactly 20 degrees. And I divide the left-hand side by the same exact number so that everything stays equal. And then I would get pi over 9 radians.
Okay, so why would we divide it by 18?
So I chose to divide by 18 because I knew that if I take 360 divided by 18, I get 20.
Okay.
So my goal here was to rearrange the right-hand side of this equation, which was originally 360 degrees. My goal here was to find some kind of operation which I could do to the right-hand side to make the right-hand side 20 degrees.
Okay.
And then I knew that if I would just do the same thing to the left-hand side, then everything would stay equal.
Okay, that makes sense.
So that's one way to do that, or you can use the following cheat code, which is that if you want to go from degrees to radians, you just take 20 degrees in radians, or in degrees. If you want to get the radians, you just multiply 20 times pi divided by 180, and that would be 20 pi over 180, which would be, if you cancel 20 goes into 189 times, it would be pi over 9 as well.
Okay. Okay.
So if you want to just have something to memorize, this would be the thing to memorize.
Okay.
Just take degrees multiplied by pi over 180 to get radians. And then we multiply by the reciprocal of that if we want to switch the other way around.
Okay. Okay, so can we go through some examples of that, doing that?
Yes. So, I don't know, let's pick a random example here. Why don't we try convert 6 degrees to radians? What should I do?
Multiply 6 by pi over 180.
Okay, so I get 6 pi over 180. And 6 goes into 180 30 times. So that'd be pi over 30. Let's try the other way around. Convert pi over 2 degrees. What should I do?
multiply pi over 2 by 180 over pi.
Okay, so the pi's cancel. And I'm left with 180 over 2, which is what?
60.
No, not quite.
Right. 90.
Yeah, 90.
My bad.
No worries. 180 over 3 would be 60, though. Which is one thing we just did a second ago, so. Okay, so we got 90 degrees.
Okay.
Okay, so is that comfortable?
Yes, that makes more sense.
Okay, cool. So like I said, you can always go back and review this table here of the super common ones. Okay, we've got 90 degrees is pi over 2, 180 degrees is pi, 360 degrees is 2 pi, 60 degrees is pi over 3, 45 degrees is pi over 4, 30 degrees is pi over 6. Okay, and these relationships are all consistent, right? If you consider 45 degrees is half of 90 degrees, well, if we look at the radians, we see that pi over 4 is half of pi over 2.
Yes.
So these are all consistent like that.
Okay.
Okay, so then today we started with this arc length example, which was a little bit complicated. But here's the basic thing that it was testing. It's testing, do we know what the definition of a radian is? So first of all, they gave us an angle measurement in degrees, and they asked us something about the arc length on a circle. Well, we know that there is a relationship between an angle's measure in radians and its arc length. Okay?
Okay.
So the first step that a student suggested was, let's take 30 degrees and convert it to radians. So we took those 30 degrees and we multiplied by pi over 180 to get the radian measurement was pi over 6.
So we used, okay, so the original angle is 30 degrees, correct?
Mm-hmm.
And then we just took that 30. Okay, that makes more sense.
Yeah, we just converted it to radians.
Okay.
Using our cheat code.
All right.
Okay, so once we had this angle measurement in radians, we know that a radian is a measurement of an angle which produces an arc length of the same number, okay, on the unit circle. But the trick for us was that the circle which was given to us had radius 2. So we had to sort of draw in this unit circle, which I did in blue here. And I said, well, I know that if this angle here measures pi over 6 radians, then I know that this length of the pizza crust on the inner circle will be pi over 6 units long.
Okay.
That just comes from the definition of a radian. And then I used a little bit of geometry to think about how we should get the length of the arc length on the outer circle. And the geometry that I said was, well, if I look at the proportion of the circle, which the yellow highlighted part takes up, versus the green highlighted part, then the proportion of the circle which gets taken up is the same, no matter how big the circle is, right?
Yes.
Okay, so if I say that this is like, the pink part is like, I don't know, 10% of the total circumference of this circle, then if I draw my pie chart a little bit smaller, right, then this will also be 10% of the circumference of the middle circle, right?
Okay.
So I use that fact to set the following things equal. I said, well, the arc length of the inner circle divided by the circumference of the inner circle should be equal to the arc length of the outer circle divided by the arc length of the outer circle, or the circumference of the outer circle.
Okay, so the outer circle is 4 pi. Okay, so why is the outer circle 4 pi and not 2 pi?
So that just comes from the circumference of a circle is equal to 2 pi times the radius of the circle. So if I have one circle, its circumference is the distance I would walk if I walked all the way around the circle.
Okay.
Right? That's what the circumference is. But if
Yeah.
I have a bigger circle, then I have to walk further to get all the way around.
Yes.
Right? It's like a track. If you have a small track that's like an eighth of a mile versus a quarter mile track, right? Then it's just like the wider the circle is, the longer it takes to walk all the way around it. Okay, so this is a radius. This is 2 pi times the radius. You might have learned pi times d at some point. Or 2 pi r is probably better. Anyways, so 2 pi r is the circumference of this circle. So the circumference of the inner circle, which has radius 1, is 2 pi times 1. So let me do that back in blue. So c equals 2 pi times 1, which is just 2 pi. And that's how I got the circumference in the denominator of the left-hand side of this equation.
Okay.
And then the outer equation had circumference 2 pi times the radius of the outer circle, while the radius of the outer circle is 2. So 2 pi times 2 is 4 pi.
Okay, that makes sense.
And that's how I got the denominator on the right-hand side.
Okay.
So this expression here on the left-hand side literally says percent of the total circumference which this purple arc length takes up in this drawing. And the right-hand side says literally percent of the total circumference of the outer circle which the pink part takes up.
Okay.
So those two things together should be equal to one another, because I know that the percentage of the circumference which the purple part takes up of the inner circle should be equal to the percentage of the total circumference of the outer circle which the pink part takes up. So that's why I was able to set these two fractions equal to each other. And then I just multiplied both sides by 4 pi to get L.
Okay.
Okay. So that's how I do that. All right. So then we talked a little bit about right special triangles. Okay, so first of all, the angles inside a triangle add up to 180 degrees. Is that familiar to you?
Yes.
Okay. And Pythagorean Theorem, is that familiar to you?
Yes. It's been a minute, but yes, it is.
Okay. So we just have a squared plus b squared is equal to c squared. Okay, so if I have a triangle, which is a right triangle, and one side length is a and the other side length is b, then I know that this side length is c, well, I have that a squared is equal to, a squared plus b squared is equal to c squared. And so if I, for example, if I know A and B and I want to figure out what C is, all I have to do is take this equation and solve for C by taking the square root of both sides. So if I did the square root of both sides, then I would get C on the right-hand side, and on the left-hand side, I would get the square root of A squared plus B squared. If I know what A and B are, I can just plug them into this thing and get C by taking the square root.
Okay.
That is the Pythagorean theorem in its entirety.
Okay.
So there were two special right triangles, which basically the reason we learn these special right triangles is so that we don't have to use the Pythagorean theorem every time. Okay, so we prove these relationships using the Pythagorean theorem. That's kind of the subject material of another class. So here's the general idea. We have a 45, 45, 90 triangle.
Mm-hmm.
Okay, so two of the angles are 45. One of the angles is 90 degrees. Well, there's a theorem in geometry which says that if we have a right angle triangle, so we have a right angle and two of these angles are equal to one another, then the sides which are across from those angles are also equal to one another. Okay, so in particular, if I just start with this bottom side length, and I know that its length is x, the theorem tells me that the side length of the other side is also x. So say this side length is 7 units, then this side length will also be 7 units.
Okay.
Okay, and then the Pythagorean theorem, which said that C should be equal to the square root of A squared plus B squared. Well, if A and B are both 7, then we would get C is equal to the square root of 49 plus 49, which is equal to the square root of 2 times 49, which is equal to 7 times the square root of 2.
Okay.
So the Pythagorean theorem tells us that if this side length is x units long, and this side length is x units long, then the other side length will be x times the square root of 2 units long.
Okay.
And x can just be any number that it wants. Okay, x could be 3, 4, 5, 1 billion. The point here is that depending on how long this side is, we know how long the other side is because it should just be exactly equal. And the last side should be equal to however long the first side was times the square root of 2.
Okay.
Okay, so we did this example, which I'll just redo. So if we know that we have the following, we have pi over 4 radians in this corner and in this corner. Okay, if I take pi over 4 radians and multiply by 180 over pi, I get 45 degrees. So these angles in these two corners are 45 degrees, and the angle in the bottom left is a right angle. So I know that this triangle is a 45, 45, 90 triangle. You with me so far?
Yes.
Okay, so the question is, if this side length is 6, what are the other two side lengths? The way I do that is the following. I'm just going to call these two side lengths x. I know that they should be equal because this is a 45, 45, 90 triangle. Right?
Yeah.
And I know that if these two side lengths have length x, then by the Pythagorean theorem, the side length, which is on the hypotenuse, should have length x times the square root of 2.
Okay.
So if I want to know what x is, and I have an equation which says that 6 is equal to x times the square root of 2, all I have to do is take both sides and divide by the square root of 2. It would cancel on the right-hand side, and on the right, or on the other side, we'd have 6 divided by the square root of 2, which, if we would rationalize the denominator, which we should, we would multiply by the square root of 2 over the square root of 2, and we would get 6 times the square root of 2 divided by 2. And then we would be able to cancel out one factor of 2 from the numerator and the denominator and get 3 square root of 2.
Okay.
Okay, so this is how we can use the special right triangle to figure out what the other side lengths are if we know one of the others.
Okay.
Okay. If you want more practice with these special right triangles and using these proportions to figure out how to find the other side, you just go on YouTube and you type in special right triangles. There will be like a million Khan Academy style videos that explain it way better than I ever possibly could and go through like tons and tons of examples. So that's how I've studied this if you want some more review.
Okay.
Okay, so then let's learn the other special right triangle. The other special right triangle is one where one of the angles is 30, one of the angles is 60, and one of the angles is 90. Okay, and the special relationship between the side lengths for this triangle is that if we consider the smallest side length, which we know from geometry, the smallest side length will be across from the smallest angle. Okay, that's geometry. So if we call that smallest side length x, then we know that the length of the middlemost long side length will be across from the 60, and its length will be x times the square root of 3. And we know that the length, which is across from the 90 degrees, will be the longest, and it will be equal to 2 times x.
Okay.
So we had this example where we were given that the length of the hypotenuse of this 30, 60, 90 triangle is 3. So in particular, we know that 3 is equal to 2x. And this equation tells us then that x should be equal to 3 halves. So I know that x is 3 halves, and that should go on where the shortest side is, right? From this other triangle. We know that x should go on this short side. So here goes 3 halves. And then we know that we should take that number and multiply it times the square root of 3 to get the side length of the other side. So that would be 3 halves times the square root of 3, which would be equal to 3 root 3 over 2.
Okay.
Okay, so this is how we use these special right triangles. So is this clear as mud, or
Yeah,
better than that?
it's pretty clear.
Okay. Cool. All right, so the next step was to sort of incorporate this into the unit circle. And we do that by using trigonometric functions. This first example wasn't even really trig related. This was a question that you could have answered after the first week of class. Was, okay, we have a unit circle and its equation is x squared plus y squared is equal to 1. Okay, so that is the collection of all points such that if we plug x comma y in, that equation will be true. Okay, so here's a picture of the unit circle. It passes through the points 1 comma 0, 0 comma 1, negative 1 comma 0, and 0 comma negative 1.
Okay.
Okay, and the question that we had to answer was, is this point 2/3, comma, negative square root 5/3 on the unit circle? And if we want to check if a point is on a circle, we just have to check if we plug it into the equation of the circle, does it make the equation true or not? So we tried plugging in, we plugged 2/3 in for x, and we plugged negative 5, the square root 5/3 in for y in that equation, and we checked if it's true. So we did 2/3 squared plus negative square root 5/3 squared, and we got 4/9 plus 5/9 equals 9/9, and that was equal to 1. And so since we wound up getting that the equation was true, we said that yes, this point is on the unit circle.
Okay.
Okay. So that's how that one worked. And then the following was really the biggest and most important thing we learned in the lecture today. Okay. Which is now going to tie the concepts of the unit circle to those concepts about angles, which we were just talking about earlier. Okay, and here's how we tie it. It all has to do with this equation here. Okay, so P of theta is a function. Okay, and what does it do? Well, if we go back to our conveyor belt system here, here's how it works. We take theta, which is an angle, okay, and we plug it into P. And P is going to take that theta and it's going to spit out a point x comma y according to a certain scheme.
Okay.
The scheme that P uses to decide which point x, y to output is as follows. It takes the angle theta. Let me clean this up a little bit. Okay, it takes the angle theta and it places the initial side is always on the positive x-axis. Okay, so the initial side is always facing directly to the right. And then we take theta and we measure it by just rotating a certain amount. Okay, and the amount depends on what number theta is and whether we're measuring in degrees or radians.
Okay.
Okay, then we draw on this terminal side. This terminal side is just a ray which goes on and on forever in that direction. And theta measures the difference in the direction between the positive x-axis and this other ray, which just goes off in this weird direction. Okay, and the function P does the following. It takes that angle theta, it puts it right here, measuring between the x-axis and our new ray. And then it checks what point on the unit circle does the terminal side cross through. Okay, so no matter where I put this terminal side, it could be here, or it could be over here, or it could even be down here. P of theta is going to output a point, and the point that it outputs is just going to be the point for which that terminal side goes through the unit circle. Okay.
Okay.
So what I said in class was that the fact that we call this thing p and that we think of it as a function is much less important than the following. What we need to understand is that for every theta, any angle that I choose, okay, if I measure it from the x-axis, from the positive x-axis, there will be a point on the unit circle which corresponds to that angle.
Okay.
Okay? So we have a correspondence between theta and a point x comma y, where if I take theta and I put its initial side on the x-axis and I put its terminal side just however far away from the x-axis theta tells me to go, then I get a point which will be somewhere on that unit circle.
Okay, so on our exam or on homework, will we be given the point xy, or will we have to find it?
So that's a good question. You know, it could really let me think about that actually. Let me check if we're going to learn something.
Okay.
Yeah, we are going to learn something. Okay, so it's going to depend. Sometimes a homework problem might say, find the point xy which corresponds to the angle. No, they would say, find the point xy on the unit circle which corresponds to the angle theta. And they'll give you theta equals 36 degrees, something like that. Okay?
Okay.
And you will be asked to find out what x and y are.
Okay.
Sometimes the question will say rather, if x comma y is a point on the unit circle and x equals 2/3 and y equals negative square root 5/3, find theta, the angle theta, which corresponds to this point if theta is measured from the positive x-axis. Okay, so sometimes they'll give you x comma y and ask you to get theta, and sometimes they'll give you theta and ask you to get xy.
Okay.
Okay, and the methodology for figuring out the thing you want to know is going to be different depending on which one we get and which one we're trying to get. Okay, so this is the relationship between the unit circle and this angle business. Is the clever thing is, rather than talking about a point on the unit circle, okay, so say I just choose this random point here on the unit circle. Instead of talking about that point in terms of its coordinates, I can say instead it's on the unit circle and the angle measure is beta. And if I know what beta is, then I can say where that point is. I say basically, I have a cannon here. I point my cannon in this direction and I shoot my bullet 1 unit away. And that's where the point is.
Okay.
So this is kind of how we're thinking of this, is we can take any point on the unit circle. It can either be defined by its coordinates in the Cartesian plane by just saying, okay, how far to the left and how far up and down is it? Or I can say rather, well, I just take an angle and I produce a hypotenuse of a certain length, right? So the point is, if I draw in this triangle here, there's two ways I can describe where the point x comma y is. The first way that you're used to understanding is, well, you walk x units in this direction, and then you walk y units in this direction. Then that's how you get to x comma y. But the other way that we can think about how to get to x comma y, rather than walking like we're walking down city streets, is sort of as the crow flies. We can say, rather than walking x units to the left and then y units up, I would rather just initially face in that direction, and I'll just walk 1 unit in that direction. Okay, so rather than walking on the sidewalk and using the crosswalk, I'm just going to jaywalk straight across the street at a certain angle and go directly to that point.
Okay.
Okay, so the next thing and the last thing we learned today was the definition of two functions. Okay, and the functions that we learned are sine of theta and cosine of theta. And they're defined through this correspondence, which I've just been talking about. So we have this green box here, okay, which says that if we have an angle theta, we can put it in direct correspondence with a point x comma y, which is on the unit circle. And depending on what theta is, x and y might be all sorts of different numbers. And depending on what x and y are, we can think about what theta is going to be. Okay? And the definition of sine and cosine is that they take an angle as an input. Okay? And sine takes that angle as an input, and it outputs the value y, where this value y is the y-coordinate of the point on the unit circle, which corresponds to that angle theta.
Okay.
Likewise, cosine takes an angle as an input, and its output will be the value x, which is the x-coordinate of that point on the unit circle, which corresponds to the value theta.
Okay.
So if I were to draw a complete picture, it would look something like this. So here's a unit circle. And I say to you, give me some angle theta, any angle theta. So say you give me theta is equal to 3 pi over 4. And I would say, okay, I don't know what that looks like, so I'll convert it to degrees. It's 135 degrees.
Okay.
I just do that by taking this times 180 over pi, right?
Yeah.
Okay, so I get 135 degrees, and I know that looks like, this looks like 90 degrees. Whoa. This looks like 90 degrees plus 45 degrees, right?
Yes.
So what I would do is I would start with my initial side facing to the right, and I would count 135 degrees. Okay, so the first 90 get me to here, right? Because that would be a corner. And then I go 45 past that is going to get me kind of like here.
Okay.
So here's theta equals 135 degrees. Okay. And then this is a point x comma y, which is on the circle x squared plus y squared equals 1. Okay.
Okay.
So what I can do here is kind of drop this point here to the x-axis. And now I can consider the following. this distance here will be this x value.
Okay.
And I said that that distance is also going to be equal to cosine of theta, because cosine of theta takes the value x, where x is the x-coordinate of the point on the unit circle, which corresponds to theta. So I could call this distance x, or I could call this distance cosine of 135 degrees.
Okay.
And that will tell me what that distance is. And then this other distance, height, this would be the value y, right? Since I know that the point here, this is just a point in the Cartesian plane, and a point in the Cartesian plane is given by its x-coordinate tells us how far left and right we go, and its y-coordinate tells us how far up and down we go. So if I want to consider what is this distance here, well, it's the same as, you know, if I were to draw this over here, it's the same as the height of the point, right?
Yes.
So this is the value y, would be how we describe the length of this side of this triangle. And y is equal to sine of 135 degrees.
Okay.
This is how we've defined the sine function. The sine function says take an angle, then sine of that angle produces the value y such that y is the y-coordinate of the point on the unit circle, which corresponds to that given angle.
Okay.
Your noise in my apartment right now. Weird. Okay. So that's pretty much it. That's where we've gotten so far.
Okay.
So the last example was, I guess we'll talk about this one. Last example was, how do we find numerically what is the sine and cosine of an angle? So if I want to find sine of pi over 4 and cosine of pi over 4, how would I do that? Well, the first step is always to draw the unit circle.
Okay. Just a quick heads up. I have to be in class in like 10 minutes.
Okay. So do you want me to finish this example really quickly, or you want to go now?
It's whatever. It doesn't matter.
Okay. Well, I'll finish this quick then. So pi over 4, if I convert to degrees, it's 45 degrees. So the angle here that I can draw on my unit circle will be 45 degrees. So I'll draw it here.
Okay.
Okay. Then the game here that we're going to play to find out what sine of pi over 4 is and cosine of pi over 4 is the following. What we're going to do is, oops, let me just draw this like this. Okay, so here's the angle 45 degrees. Since I'm interested in knowing what sine of pi over 4 is, and I know that sine of pi over 4 is equal to the y-coordinate of this point, and cosine of pi over 4 is equal to this x-coordinate, then all I'm going to do is figure out what is the point x comma y, which is on the unit circle, which corresponds to the angle 45 degrees, and then I will know what is the value of sine of pi over 4 and cosine of pi over 4. Okay, and the way I do this is by using my triangle rules. I just drop a line from here to the x-axis, and I know that since that's a vertical line and the x-axis is a horizontal line, this is a 90-degree angle. And I know since the angles inside a triangle add up to 180 degrees, and so far I already have, why is that happening? So far I already have 45 plus 90 is 135. I know that this angle should be 180 minus 90 minus 45. That's also equal to 45. So I know this angle here is 45 degrees as well. So I have a 45, 45, 90 triangle. And my question to you is, do I know what one of the side lengths is of one of these side lengths?
Wouldn't it be the pi over 4?
Pi over 4 is the angle.
Okay.
My question is, do I know one of the side lengths? Here's one thing we can say. We know that the x-coordinate, the x is kind of what we want to know. So this is a question mark. And the y-coordinate is going to be this length here. So this is also a question mark. So really our only choice is to say, do we know what this length is here?
Yes.
And what is it?
Good question. I have no idea.
What is this circle that we've drawn? What's its name?
A unit circle or the circumference?
Yes, the unit circle.
Okay.
And what is the special property of the unit circle that really makes it the unit circle?
That it's broken up into 4 right triangles?
Well, that too, but more importantly, how do I distinguish this circle from this circle, which is slightly bigger? What's the special property of the unit circle?
Isn't it like 2 pi?
2 pi is the circumference.
Okay.
But there's even something we can say about the unit circle. The unit circle tells us exactly how far this distance is. What is the radius of the unit circle? Well, the equation is x squared plus y squared equals 1.
Yes.
So what's the radius? Should be
1.
r squared is 1, so therefore r is equal to 1. So if the radius is 1, I know that this length is 1, and this length is 1, and this length is 1, and any length which goes from the center of the circle to the outside of the circle should be 1. So in particular, the length which is on the hypotenuse of this equation is 1.
Okay.
And that tells me that if I want to find out what the other sides are, if I say this one's x and this one's x, I know they should be the same since it's a 45, 45, 90 triangle. I know from the 45, 45, 90 triangle that 1 should be equal to x times the square root of 2.
Okay.
And therefore that x should be equal to 1 over the square root of 2, which is just square root of 2 over 2.
Okay.
So this point here is the point square root of 2 over 2 comma square root of 2 over 2, and therefore cosine of 45 is equal to the x-coordinate and sine of 45 is equal to the y-coordinate.
Okay.
All right, and that's that. I don't want to keep you for your class.
Okay. Perfect. Thank you so much. This made so much more sense.
Okay, yeah. If you get behind like that, it can be hard to get back into it if we, talk about something new on day 1 and then you come back in on day 2. So best thing you can do for yourself there is probably just watch the the previous lecture before moving on to the next one.
Okay, yeah, I'm gonna watch it after this class and try
Okay.
myself up. So, great, thank you.
Yep, no problem. My pleasure. Have a good day.
You too. Bye.
Bye.